I wanted to talk about, since we have some time today, is this is something that my boss brought up with me at one point, which I thought was pretty interesting. I'll explain what it is first. So there's this concept or theory, I'm not really sure what the right term is, of what's called the Dunning-Kruger effect. So it's this idea, if we graph somebody's confidence on the y-axis here against their knowledge, how much do they actually know from, I know jack squat versus I'm a guru in my field and I know everything. The Dunning-Kruger effect, uh, the idea here is this is what that curve follows. So for some reason, the people who seem to know the least seem to have the highest confidence, and they tend to be the loudest person in the room. So if you are hanging out at the top right here, this is what we call the peak of Mount Stupid. You don't want to be there. You don't want to be at the peak of Mount Stupid. But then what ends up happening as you gain knowledge in whatever industry you go into, you start to realize, you start to descend the peak of Mount Stupid, and you are learning more in your field, but you're really starting to learn, wow, there's so much I don't know. And you start to have these self-doubts of, man, I'm just never going to learn this stuff. I'm never going to be as good as this other engineer that I'm working under. They seem to know it all, and I don't get it. And this is called the Valley of Despair. And I've worked with engineers who've been in the Valley of Despair, and it's kind of disheartening because they really just lack a lot of that confidence, because they've made enough mistakes that it's really just shot their confidence. But there is hope. Then we start to get on the upside of the Valley of Despair, and we start to enter this slope of enlightenment where you do start learning more about whatever industry you're in, and at the same time you start to build this confidence that, hey, I actually do know this stuff. And then finally at the end we enter the plateau of sustainability, and now you know a lot about your field and you have the confidence to talk about it. And importantly, you have the confidence to know when you don't know things. And hey, it's okay to not know things. I thought this was kind of an interesting concept because my personal experience was nothing like this. So this was my curve coming right out of college. So a little background. When I was in college, getting my engineering degree at Gonzaga, I always did very well in school. I was very good at school. I understood the math and the theoretical concepts, everything we're talking about. I wasn't much of a hands-on engineer. My roommate, who was also in the mechanical engineering program, he was the exact opposite. He struggled more on the mathematical side, but he was totally a hands-on engineer. And when he just wanted to build something, he would just go build it. And in my eyes, I looked at my roommate Dave, and he was the real engineer, and I was this fake engineer. And as soon as school was over, the gig was up. I was going to get found out as this massive fraud. And of course, that's not what happened, but that's kind of the mindset I had leaving school and going into the workforce. And so I had low confidence and I didn't know anything. What didn't help was my first job out of college is my immediate supervisor was not a great mentor. And he kind of made me feel stupid for not knowing things. Even in retrospect, I know I shouldn't know those things, but at the time, I don't know. It didn't make me feel good about my job or what I was doing there, and that didn't help with my confidence thing here. But around the age of, let's see, I was probably 26 or 27, so I'd been in the industry about 5 years. Then I started realizing, well, hey, maybe I do actually know some of this stuff. Correspondingly, this was after I had started at McKinstry, where I'm still at. At McKinstry, I actually found a really good mentor, and that made all the difference. And so eventually I got to this plateau of sustainability. Don't follow my curve, but also don't go to Mount Stupid. Try not to get into the valley of despair. Stay humble. It's okay to not know things. All right. All right. Other brief thing I wanted to talk about is another project I worked on a few years back. This was with the Spokane Transit Authority at their maintenance garage here in Spokane. So this building is, it's right by REI, off Monroe and Boone, kind of a funny shaped building. But this is their primary bus maintenance facility, about 220,000 square feet. It's a good size building. It's essentially a bunch of big open bays where they're doing bus maintenance. And because of that type of work, working on vehicles, they require a lot of ventilation. And as we know, a lot of ventilation means a lot of energy. And that's just because of the vehicle fumes that are going to build up in the space. So as they pull their buses into this garage, sometimes they need to have them running for various reasons, and you need to provide a lot of ventilation air to dilute that and keep the indoor air quality at a good level. Their existing systems, before we did anything, they had a number of 100% outside air units on the roof with gas heat. And when I say 100% outside air, I'm just saying there's no recirculation of air. So if it's bringing in, say, 10,000 CFM, that is all ventilation air. And when it's cold outside, they're going to use their gas heaters to heat that air up to about 65 degrees and then send it into the space. Because if it's 0 degrees outside, because we get that cold here in Spokane, we don't want to be dumping 0 degree air into a building. So we heat it up to a moderate 65 degrees and send it out. There's no cooling systems. So if it is a 100-degree day, then they're getting 100-degree air. But that tends to be easier to deal with than extremely cold air. These outside air units are paired with exhaust fans that are sized for the same CFM, same amount of airflow, because we need to exhaust just as much air as we're bringing in. If we're putting in 10,000 CFM of outside air, we have to exhaust the same amount of air. Otherwise, we're going to end up pressurizing the space. So we have to keep it balanced. These were constant volume systems. I didn't mention this in the notes, but they were also manually turned on and off. So when they get there in the morning, they flip a switch on the wall and that turns the units on. Everything just runs at full air volume. And when they're done for the day, they go and turn them off. Unrelated to the mechanical systems, they also had high intensity discharge lighting and a leaky envelope. I care a little less about that stuff because that's not mechanical engineering related, but we did do it as part of this project. And we have talked about lighting and envelope as part of this class. This is what one of those units looked like. We have the intake right here. So this is a weather hood to prevent water and snow from getting pulled in. So it's pulling in air through that angled end. Then there's a gas heating coil inside here and a supply fan, and then it's discharging air out the bottom. So there's a whole bunch of these up on the roof. And then we also had a bunch of exhaust fans that have to be matched up with these outside air units to keep the building in balance. This is what that looked like below the roof line. So if you imagine coming down from this unit right here, that ductwork comes down, does a T, and then it blows out all of these supply air registers into the space. And then we had some crappy lighting here. This kind of gives you an idea of what the facility looks like. Big, open, high bay spaces, lots of room to pull in their buses and work on them. What we did to save energy here, we replaced all of their 100% outside air units and their exhaust fans, and as part of that, provided new controls. I mentioned earlier that they had to manually turn on their equipment on and off, which you can imagine there could be situations where they forget to turn it off. And now the unit is running all night long when it gets really, really cold at night. Um, maybe they forget to turn it off over an entire weekend. That's multiple days where that equipment is running and using energy. So the new controls they got takes away the manual nature of it and now automates it on a schedule. There's still 100% outside air units on the roof. It's the same concept as what they had before. But what we found out we were able to do is we were actually able to size them for about half of the airflow as before. The short answer for why we were able to do this is when we looked at modern code for how much ventilation air is required for this type of space, it turns out they were way over ventilating. I mean, by a massive degree. And so we were actually able to downsize all of the equipment to about half. And by doing that, that reduces our peak fan KW and our peak gas use, because now we don't have to heat as much air. Across the whole building, we went from 316,000 CFM of supply air and exhaust air down to 153,000. So a substantial decrease. And then horsepower, which we've been talking about fans and horsepower lately, not quite half, but still 311 to 204 horsepower is a substantial decrease. So right off the bat, that alone would save a significant amount of energy. But we did more than that. We also made these same systems variable volume systems. So we were able to stick VFDs, which you're now all experts on. We put VFDs on all of those fans. And so now we can dynamically adjust the ventilation and the exhaust air based on what's going on in the space, where we're measuring carbon monoxide and nitrogen dioxide levels in the space. And the reason we're monitoring for those gases is that is what the bus fumes are going to be putting out. So we have all these sensors in the space measuring those two compounds. And if at those sensors we see a high carbon monoxide or a high nitrogen dioxide, and it's important we're saying or, because we're going to go to whichever one is worse. If the sensors detect a high level of either, we're going to turn our fans to high speed, going to provide a lot of ventilation, 100% flow. But if both sensors read low, and this is an and statement because both need to be low, then we're going to turn down to 50% flow. And this 100% and 50% is in relation to this already reduced airflow. So if we're at 50% flow, we're at about 25% flow from what they used to be at back when they were constant volume systems. By doing this, we're going to save even more fan energy and even more gas energy when buses aren't actively being worked on. The old method of controlling these were constant volume, they flip a switch and it just runs all day. But they're not pulling buses in and out all day. And they might pull in a bus or a few buses, park them, turn them off, and then work on them. And that way, when they're not actively running in the space, we can turn the fans down. And we installed some new LED lighting fixtures. Again, I'm not very focused on that part of it. And we tightened the envelope with some insulating spray foam. Basically, we went to where the walls meet the roof, because that's always a point of a lot of infiltration. A lot of air gets into the building through that part of the building. And we put some insulating spray foam, tightened it up, save energy that way. Here's what one of those new units look like. So fundamentally, it's doing the same thing. We have our intake on this side. We have a gas heater in here. This is our gas piping feeding the unit. There's a supply fan somewhere in here, and then it's blowing down into the space. New exhaust fan. You can see because we downsized the exhaust fans, you can see the footprint of the old fan. And so what we did is we put what's called a curb adapter, basically just a fancy sheet metal transition piece that'll get us from this big old footprint down to our new smaller footprint. So that shows you how much smaller that fan is versus the one that was there before. And then we have our CO sensor and our NO2 sensor. And you can see they're actually located at different heights. So one is high and one is low, just because those compounds tend to rest at different levels. One other thing, this green button right here, I mentioned that this equipment up on the roof, the outside air units and the exhaust fans, those were scheduled now after we're done because we gave them new controls. But if there was ever a scenario where the equipment wasn't running and for some reason they had some off-hour operation, a maintenance person could come in and push that button and turn that system on for 2 hours. But then after 2 hours, it would turn back off. So we still don't have the potential problem of them leaving it on all night or all weekend. So the summary on the savings side, so their baseline condition, so this is what they were using before we came in. They were using about 1.6 million kilowatt hours per year and about 205,000 therms per year. And you don't know enough to really understand magnitude. You know, is that a lot? Is that a little? That is a lot of energy. But it's also a very large building, 220,000 square feet. The EUI, 118 kBTU per square foot per year. That is also a very high EUI. And that makes sense because they have so many of these 100% outside air units, and that takes a ton of energy to treat that ventilation air before sending it into the space. And this resulted in about $413,000 per year that they are paying Avista to provide their electricity and gas. That's a big utility bill every year. When we were done, their new electric use was about 660,000 kilowatt hours, about a 59% savings. Gas use, 115,000 therms per year, 44% savings. EUI was about half of what it was, 61, not too shabby. And their annual utility costs, $293,000 per year. So the final savings at the end of the day, as a result of this project, $120,000. And you might notice that, well, hey, we're saving 59% of their electricity, 44% of their gas. Why is the final dollar savings only 29%? Does anyone have any guesses, thinking back to when we talked about utilities?
The peak demand charges.
There you go. So what's not shown here is the peak demand. And peak demand is very difficult to quantify the savings for. It's because that is only tracking that 15-minute period every single month when they're peaking at that demand. And that's really hard to both model in our energy model and to try to guarantee some level of savings. So that's right. There probably were some demand savings there, but the demand savings would have been substantially less. The total cost of the project was about $2.4 million. But what we did is we helped them secure a Department of Commerce energy grant for about $540,000. So we developed this project and then worked with STA to help them apply for this grant. And when they saw those numbers that I just showed you, that was a pretty easy case to say, this is a really good energy project, and hey, we're going to give you $500,000 to help you execute it. On top of that, Avista gave them $300,000 in utility incentives, and that includes both the mechanical side and the lighting side. So the client cost at the end of the day, we shaved $840,000 off of that, and it ended up right around $1.5 million. And I mentioned the utility savings, $120,000 per year. One thing I didn't mention earlier was the operations and maintenance savings. Sometimes we go into buildings and we find out they have just been throwing money at equipment to keep it running. And as a result of us replacing that equipment, we can also claim some operations and maintenance savings. So that equated to another $11,600. And we ended up with a simple payback of 11.9 years, which in this climate, speaking of Washington specifically, that is actually a really good project. 12 years might sound like a long time for something to pay back for itself, but from all of the energy projects I've been involved with, this is a very, very good one. And from STA's perspective, they got all this new equipment. They got a new control system to control all this stuff. They know they're still going to be around in 12 years. And they had a good chunk of this paid for by the energy grant and the utility incentives. So this was a big win all around. This was a really good energy project. Any questions on that?
Your last presentation, when you talked about the actual temperature versus the perceived temperature, would putting a system like that in a building that has a lot of outside airflow be a good idea or another option?
Yes. And actually, so what you're talking about are infrared heaters. These units, I'm going to scroll back. So these units, I mentioned they're only outputting 65-degree air. That is not warm enough to heat your space. You can't actively heat a space with 65-degree air unless it's significantly colder than 65 degrees. So what we didn't touch on this project is they already have a number of infrared heaters in their maintenance bays. So the way that works is the infrared heaters are the primary heating devices that are maintaining the space at, say, 60 or 65 degrees. These units are strictly for ventilation air, and we are essentially just delivering neutral air, just because we don't want to dump super cold air on a bunch of people. So yeah, you are right. Infrared heaters are a great application for something like this, and those are already installed and they were already working pretty well, so we didn't replace those.